Hello everyone, I'm going to be recording solutions for the extra problem in the rotation module. This is for chapter 11, and this is actually inspired by a homework problem, but it's an old exam problem, and what you're given is information about a projectile. Here it is. It's projected with some initial velocity at angle theta close to the surface of the Earth, and comes back here and lands on the Earth. And from kinematics, we know that we can get this position vector. And it's given to you in the problem as a function of time. Initial velocity in the x times time for position. Acceleration integrated twice due to gravity, and initial velocity times time. And in this, the origin of the coordinate system was given to you. So at time equals to 0, you are at the point of release. So this would be 0 and 0 at time equals to 0, meaning you're at the origin. All of these things are known here: initial velocity, g, and you also know the mass. And it says, for the point particle, which is what this is, find the angular momentum vector as a function of time with respect to the origin given. So of course, for angular momentum, we need to talk about the origin, or have a defined origin, and so it's here, which coincides with our position vector here. And for a point particle, we talk about angular momentum as r cross the linear momentum mv. So I already know position as a function of time as a vector quantity, and what's left is really to find velocity as a function of time. So my first step is to find the velocity by taking the first time derivative of the position vector. The derivative operator will act and be distributed through on each component of the vector. So through here and through here. So I'll go ahead and do that. Get rid of these brackets. Just kind of cheating a little bit and throwing that derivative operator in. And v naught and the theta, those are constants of the initial conditions that you're given, and they're knowns. And so the first time derivative there will just give you v naught cos theta, which makes sense because in the x, of course, we have constant velocity. And then the time derivative here will give you, there's a t squared and a t, so plus minus gt plus v naught sine theta, and this is the velocity in the y direction, where we do have acceleration, which means we have a time dependence there. And this is my velocity vector. And now what I'm going to do to find the momentum vector is to use that here in the cross product and r here in the cross product. And I'm actually going to find this by taking the determinant. Now I can use that formula for the cross product, or I can take the determinant. It's up to you. I prefer the determinant, so I don't have to look up any formulas. And so what I'm going to be doing is putting the x component here for r, and the y component here for r, and of course the z component is 0. That's my first vector. And then my second vector is m times v, so I can't forget that m, but here's my v, so let me go ahead and write in my m, just like that, and I will now write in the second vector here, m times v, and then 0 there, so this is a little too big, let me shave that down. And then looking at the determinant, the x gives me 0, the y gives me 0. There's only going to be a z component that exists And so at the end, I'm going to end up with just z hat, and it's going to be v naught cos theta times time, so this times m minus gt plus v naught sine theta minus this times this, excuse me, minus g over 2t squared plus v naught sine theta times m v naught cosine theta. I can sense there's cancellation in here, so I'm just going to kind of go for it and multiply everything through. I'll get minus g t v naught cos theta, another t in there, and an m, plus v naught squared cos theta sine theta, an m, and a t. Over here, I'll get a plus g over 2 t squared m v naught cos theta, a minus m v cos theta v naught sine theta t, so it becomes squared sine theta t. And that's all in the z hat. Let's look for cancellation now. Like terms. So these are like, there's one is 1, minus 1, and 1 is plus 1/2 of gt squared m v naught cos theta. And then these two are like, and it looks like they're exactly canceling. Nice. So those blue ones will exactly cancel, and the pink ones, this will be minus 1 plus 1/2, or minus 1/2 of that quantity, g t squared v naught m cos theta. Now I'm just going to check my head that I did everything right here. This times this times this times this, and this times this. Okay. And I am done. So let me go ahead and box. This is the angular momentum vector as a function of time. Looking good. So you can see that it's always going to be pointing in the negative z hat direction, which is into the board for all time. And then my next step, is to find the net torque acting on the particle with respect to the same origin as a function of time. So oftentimes we do this step just so I can at the end compare the relationship that says that is that the net torque acting on the system is equal to the time derivative of the angular momentum vector. So let's have a look at that. And let's find the net torque first, and then we'll just really be checking if these things agree with respect to one another. So this is actually easy, because if I choose an arbitrary point here for my particle, there's only one force acting on the particle at all time. It's gravity. And so if I'm thinking about the net torque acting on my system for part B, the net torque will actually just be given by the torque due to gravity. And so I'm literally going to be looking at torque as R cross F, where from gravity, this is the force of gravity, and the force of gravity, of course, is minus mgy hat with the coordinate system given in terms of this position vector. And so R is the position vector, and F here is gravity. And that's the net torque, only one force. super easy. So I'm going to do the determinant again to get R crossed with minus mg y hat, the force, which is my torque. So I'm going to write the force in first because it's so easy. And then I'm going to, actually I'm just going to copy what I have here for the position vector, that I used it in the angular momentum vector. Make it a little bigger. Okay, and then again I'll have 0x, 0y, and that leaves only a z hat component. So good strong start because my angular momentum's in the z. And I'll have first this times this minus this times this. So that second component will be 0. So it's really just this first one, minus mg v naught cosine theta times time. That is the net torque acting on the system, i.e. the torque from gravity. So that's part B. It seems pretty straightforward. And then I ask, do the results from 4A and 4B agree? And this is really what I'm getting at for part C over here. Part C is really asking, do these agree with each other? Now that I've found them separately. And so I'm going to take the time derivative of my angular momentum vector. The only thing that's not constant in here is the t squared. Of course, z hat is a constant too, so that becomes 2 times t. And then of minus 1/2 g 2t v naught m cos theta z hat. The 2's will cancel, and I'll get minus mg v naught cos theta times time z hat, just upon reorganizing things. And so the time derivative of my angular momentum vector is here, and I can see that it is the same as the net torque. So let me highlight that a little bit better. Got a little washed out, but you can see that it's the same as the torque. And so they do agree up to theory. And that's what that means. Do they agree? Okay, so now that we've played around with that a little bit, what's going to happen next is your particle's now going to have a collision with and stick to a thick ring of mass m that has a thick pin through its center. So here's just kind of an example of a couple scenarios that could happen. You're going to place this thick disk. So this is supposed to represent the pin right here, and this is the thick disk. And you're just going to place it somewhere along the projectile's path here. And let's see exactly how. So it's going to have a collision with and stick to it. So, and initially this thing is at rest, and you're given information about its inner and outer radius. So its inner radius is r/2, and its outer radius is r. So you can think about it, here we go, as just kind of this thick ring. Maybe that's the best way to think about it. With an inner radius r/2 and an outer radius of r. And it has a thick, it's been pinned in the center, and you can think about it as a massless pin. It's just there, like it's saying in the footnote. The pin is thick, so when the particle has a collision, the center of mass of the ring particle system is on the pin, causing no torque from gravity on the pin mass system when the center of mass changes. So oftentimes when you have a collision, you're trying to meet the condition that sum of torques is 0, so you can have conservation of angular momentum. This is similar to when we had sum of forces 0 for conservation of regular linear or translational momentum. To do that, I've made the pin in here very thick so that when I stick my little mass here, the center of mass will change from being in the geometric center with the addition of that pin or mass that's stuck to it, and maybe we'll shift the center of mass a little bit when that's where gravity acts, and it could create a torque. So I've made the pin here very thick so that that doesn't affect anything, even if it changes a little bit. So before I really get into this, it actually asks me to find the moment of inertia of the thick ring about its center of mass. So center of mass through the center here. And it says it has a non-uniform density. So I'm going to focus on that before I spend too much time thinking about the fact that I'm going to have a collision. Let's first find the moment of inertia. The moment of inertia is generally this, where I'd like to recognize that we're talking about integrating the moment of inertia of infinitesimal rings to make this thick disk. So the moment of inertia of a ring, if you remember, is just mr squared, and this is for one of the internal rings. So what I'm saying now is that one of these internal rings has a mass of dm and has an inner radius of r with respect to the center of mass. And that's what I'm integrating over here. So I'm going to plug in dm and just work from there. So I have the density dm, dA is sigma, and it's non-uniform. The d area for rings to make a disk is 2 pi r dr. I feel like we've gone over that quite a bit. And this gives my dm to be cr cubed, 2 pi r dr, and I can combine these r terms to get 2 pi c r to the 4th dr for my dm. Once I have that, I can kind of right away plug it into here, but I'd actually just like to find my c first. So I'm going to integrate here and here from 0 to the total mass of the ring, which would be from here to here, the whole ring, which means from the inner radius to the outer radius to complete the ring, r over 2 to r. So I'll get m minus 0 equals 2 pi c, which is a constant of the integral, and will come out. And then I'm integrating r to the 4th, which will become 1/5 r to the 5th evaluated between r over 2 and r. And so m will equal to 2 pi c over 5 r to the 5th minus r to the 5th over 2 to the 5th. So I'm going to hold space for that for a little bit, and then I'm going to kind of focus on actually doing this integral now. I is equal to dmr squared, which is 2 pi c r to the 4th dr times r squared. That's my dm. And I'm going to go ahead and pull that 2 pi c out because it's constant, and then this 4th and this squared will become r 6th. And this is then 2 pi c integral of r to the 6th dr, and I'm integrating over the ring from r over 2 to the outer radius r. So looking at this, I am going to go ahead and solve for 2 pi c over here. Before I do, I'm going to acknowledge that I can write this as r to the 5th, 1 minus 1 over 2 to the 5th. And then I'll just straight solve for 2 pi c. It's equal to 5m over r to the 5th, 1 minus 1 over 2 to the 5th. And I'll be able to plug that in here pretty easily. But first, I am going to finish the integration. And this will become 1/7 r to the 7th, evaluated between r and r over 2. And so altogether, I'm going to have 2 pi c, which was this, 5m r to the 5th, 1 minus 1 over 2 to the 5th, 1/7 r to the 7th, so I get a 1/7, and then I'll get an r to the 7th minus r to the 7th over 2 to the 7th. Now I'm going to get some cancellation when I pull out an r to the 7th term in here, because this can be written as r to the 7th, 1 minus r to, 1 over 2 to the 7th. And so I'll get r to the 5th canceling with r to the 7th for r squared, and I'll have 5/7 m r squared. And this will include this, 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 and this. And then I'll have just this kind of ratio of differences, 1 minus 1 over 2 to the 7th over 1 minus 1 over 2 to the 5th. Now, I could simplify this a little bit if I wanted to. Multiply both this by 2 to the 7th over 2 times 2 to the 7th. Do I want to do that? I don't know. I'm going to stop right now and just leave this as I. This could be my final answer. Maybe I'll simplify it a little bit and see what I have to do with it later on. But for now, that's good enough. Oops. So for now, that's good enough for me. Here it is. I've found the moment of inertia of this thick ring. Now, let's deal with it. So the idea is for this thick ring, I'm going to be placing it somewhere along the trajectory of the particle so that I have a collision. And it said earlier, it's not just a regular collision, it sticks to it. Other important pieces of information is a thick ring starts at rest before the collision. And it says you're free to place the thick ring along the trajectory of the particle only so that the collision with the particle will always be at the same place. So what this is telling you is that the particle is going to always hit it right here on this outer edge. This is for ease of calculation later on. It's not just to be picky or weird. But here's an example of where you could do that. You could put the thick ring here, or you could put the thick ring like this. But either way, you can see that it's having the collision. The particle's hitting it there on the very outer left-hand edge. And so this is a requirement. And it shows you these possible collisions. And then it says, well, for collision 1, will the disk mass system after the collision be rotating clockwise or counterclockwise? Now, I can look at this and see that it's going to want to rotate this way after the collision. And here I can see that after the collision, it's going to want to rotate this way. So I'm going to put my answers in. I'm going to justify it later, though. Okay, so a clockwise rotation for collision 1 and a counterclockwise rotation after the collision for case 2 there. Now we're going to come back and make sure that makes sense. Now, I just know this by being on the planet and observing things to know that that's how that works. And now let's kind of move forward. Find a general expression for the angular velocity vector omega for the disk and the stuck-on particle after the collision as a function of time. Now, what this is coming from is that we're actually saying that angular momentum is conserved here. So whether you recognize it or not, I gave you this information that the sum of torques would be 0 after the collision by saying that after the collision I have this thick pin, so if the center of mass changes, the net torque on the system would be 0. As long as I'm defining my system, so if this is the thick ring and this is the particle where I'm having a collision, as long as I define my system to be both the thick ring and the particle, any force of the collision becomes internal, and then the net torque will therefore become internal as well, which means that I have conservation of angular momentum. The one worry would have been if the center of mass changed, because I do have a pinning force and gravity acting here. If the center of mass had shifted a little bit to be like here, that would have created a net torque. But again, I made that thick pinning ring very thick so that it wouldn't do that, and I can meet this condition. So before the collision, remember what I have is this, maybe this thing is coming in with some r with respect to the origin. I have a point particle that has some angular momentum. So I certainly have the angular momentum of a particle. And I do have the possibility of the rotating rigid mass. If it was moving initially, rotating, it would have had some initial angular momentum as well. And this is the angular momentum, of course, not for the point particle, but a rotating rigid body. But it wasn't rotating initially, so this was 0. And then after the collision, it sticks together as a single rotating rigid body. So I can write it like this, where this is I net, and I net is the combined moment of inertia for M and M. So we'll come back to that. Oh, actually we won't. I will be what we found earlier, which was I of the thick ring, plus mr squared. The moment of inertia of a point particle is mr squared. Here, I'm going to be defining the axis of rotation through here, and my distance away will actually be the outer radius r, mr squared. So that's the net moment of inertia of the system after the collision. Just FYI, if I had included this just would have been I of the ring itself, but it's not. So the angular momentum of the particle before, as it's coming in, equals the angular momentum after the collision of the combined mass. Now I have to be careful here because what I've done is to define the moment of inertia with respect to this axis right here, which means that all of the angular momentum is also defined here for omega final and everything. So normally when I had talked about the moment of inertia of the particle, I had actually found it before. Let's scroll back. Right, I found it as a function of time. Oops, right here. But that was with respect to this origin. Now I'm talking about having an origin here where my ring is located. It's a different r vector. So when I talk about the angular momentum of the particle, r cross m times v, I'm going to be talking about a different origin for this r vector entirely. Let's take a look. So the position vector will be with respect to this origin, wherever it happens to be, will be minus the outer radius in the x hat direction. So my new r vector is minus r x hat. The velocity vector is independent of the origin. And so I don't have to worry about rewriting that. I have the velocity vector, so that's great. And again, that just has to do with the fact that, even when we talk about the velocity vector as a function of time, we're actually talking about it like this, right? It's independent of the origin. It's just related to the location of the particle. So I will be using my velocity vector. Let me go back and grab it. Velocity vector, where are you? Oh, well, it's kind of here. I'll have to ignore the m acting on it. Well, no, I won't. I need mv again. So never mind. Here's my mv. And so I'm going to find the initial angular momentum of the particle now with respect to a new origin. X hat, y hat, z hat, r cross mv minus r x hat 0, 0. mv was mv naught cos theta plus m minus gt plus v naught sine theta, 0 for the z component. In the x, there's all 0. In the y, it's all 0. That leaves only the z. And for the z, I'll have this times this minus this times this. So the second component is 0. So I'll just have z hat minus r m minus gt plus v naught sine theta. That's the angular momentum of the particle. I could reduce it a little bit. I don't see the need right now. So I'm just going to hold on to it. Well, actually, I'll multiply through. Why am I being lazy? Okay, so this becomes positive rmgt minus rm v naught sine of theta z hat. And that's the initial angular momentum of the particle. That's this, and that's going to go into my conservation of angular momentum on the left-hand side. It's the only term. And then finally, I'm going to be actually solving for this omega final. So let me go ahead and bring that down through here. Omega final will be equal to the angular momentum of the particle, which I just found before it collides, divided by the net moment of inertia. So this will be rmgt minus rm v naught sine of theta z hat divided by I net, which was I of the ring plus little m r squared. So let's go back and find that I of the ring. Grab it. Ooh, I did make one little mistake here. I always do this. This should have been a capital M, not a little m. Lord knows why I always do that. Silly me. Little m, big M, hard to keep track of sometimes. But anyhow, that's the moment of inertia of the ring. Let me kind of get in there a little bit better. And get rid of that black little line. I'm going to go with that. So again, that's the net angular momentum, I of the ring, plus mr squared, little m. And that, my friends, is the angular velocity vector for the final collision after the collision. And look, you can see it can vary depending on what time it is between a positive and a negative z hat value. This is what ties us back into this. There's a time it's going to give a clockwise, and there's a time it's going to give a counterclockwise rotation depending on how it hits. This recognizes that because the minus z hat direction will give the rotation like this, and the positive z hat direction will give a rotation like this, clockwise. So there's a time that these make sense. So let's make sure it makes sense. It says, at what time, call it t0, will the angular velocity be 0? Well, the angular velocity is 0 when rmgt equals rm v0 sine of theta. Or, and we're supposed to call that t0, when t0, the rm cancels, equals v0 sine theta over g. Now, I don't know if you remember this from before, but this is the time it takes to get to the top when we worked kinematics. So this is actually the time at the top of flight. If you placed your thick disk here and had a collision with it here at the top of flight, there would be no angular momentum. It would just come in and hit it like that. And that's it. It wouldn't cause a rotation. Down here, it's hitting up. Over here, it's hitting kind of down on the side. So at the very top of flight, that's where it's 0. So to the left of it, you're having a collision that's going to cause a clockwise rotation. And to the right of it, you're having a collision that's going to cause a counterclockwise rotation. So we should be seeing that. When t is less than t0, right? So that's smaller than what makes it 0. It's dominant negative. It's in the minus z hat direction. Then that means that I'm making a did I mess that up? I did mess it up. Oh, I messed it up. I messed up by minus sign. People, don't hate me. I dropped this minus sign. Did I? I did not drop that minus sign. Damn it, I'm off by minus sign somewhere. Where did I lose you minus sign? Sorry, people. How does a person lose a minus sign? Oh, I'm good. Oh gosh, sorry. All right, did not lose a minus sign. A little moment of panic there. Okay, then minus z hat is associated with clockwise. This jives with kind of this picture that I had before. When time is less than t0, like maybe I'm here and I'm coming in, and you can see that this is going to go ahead and create a clockwise rotation for a point particle having that collision for something at rest, versus here, say I'm coming in, hitting it here, this is where I'm supposed to. This would create, again, the counterclockwise rotation, which is associated with the positive z hat. So So did not lose that minus sign. So for t greater than t naught, meaning t is larger than this term effectively over here, you'll have positive z hat, which leads to the counterclockwise. So this jives with what we saw before. And that's what this next part was asking for. What is t naught? Got it. And does it make sense with our previous answers? It says to show specifically where it occurs. I did that. And yeah. So just acknowledging this is really t to the top. Right, I hope you enjoyed that. Have a great day.